Today we're looking at lab number 4, Ohm's Law and Power. And Ohm's Law is one of the fundamental laws governing electrical circuits. Also, we're going to be using 3 resistors, and what we'd like to do is double the resistance. So we'd like 2K, 4K, and 8K. Unfortunately, they're not manufactured in those sizes. Now I've gone out on the internet and I've found you a table with the standard resistor values. So this is for plus or minus 5% tolerances. So you can see that we have a 2K resistor, and then I wanted a 4K, so the closest I had was 3.9K. And doubling the 4K would give me 8K, and the closest that is available to us is the 8.2K. So when you're designing circuits, you can only use resistor values of a standard size because that's all they manufacture. We also have to be mindful of the wattage of these resistors. We're going to be using quarter-watt resistors. And we also need to know how much power is going to be dissipated by each resistor so that we do not exceed its wattage rating, or else it'll overheat and fail. I would highly recommend Sham's Outline Basic Electricity 2nd edition if you're not going to buy a textbook. And the chapters that we're going to be looking at, we're going to look at schematic diagrams, and then we're going to look at the electric circuit, resistance, fixed resistors, Ohm's law, and electric power. So table 2-7 gives you examples of letters used on schematic drawings, and you can see that R is for resistance. And figure 2-2 gives you standard circuit symbols, and I wanted you to notice the symbol for the fixed resistor. So chapter 3 of your textbook talks about Ohm's law and power, and that's what we're doing our lab on today. And figure 3-8 shows you the Ohm's law circle. Now I've put it in a triangle on the front page of your lab for you, but you can see the 3 different arrangements of Ohm's law: I equals V over R equals V over I, and the standard format V equals IR. So on the front of your page, I've gone out on the internet and I found these nice little graphics for you. You can see that V is equal to IR, which is how it's commonly written. You can rearrange the formula for I equals V over R, or you can solve for R if you know what V and I is. Now the power formula is very similar to Ohm's law, but power equals I times V, and can be rearranged for I equals power divided by voltage, and voltage is equal to power divided by current. So you can see you can rearrange these formulas around, and if something is unknown, say you did not know what V is, you could substitute V from Ohm's law into the power formula, and then the formula becomes I times R, so the formula becomes power equals I squared R. So on the final graphic that I give you, you can see that power is equal to R times I squared. So that was the rearrangement of the formula that we just did. There's actually 12 of these different formulas. Rather than memorizing them all, I just highly recommend you remember Ohm's law as V equals IR and power equals I times V, and then just rearrange them as you need them later on rather than trying to memorize all 12 different formulas. So you can see on the next page we want to know the model number of both the DC power supply and the digital multimeter. As before, don't bother with the serial numbers because they're a little hard to find and they're usually on the bottom of the equipment. We're also going to be using a 2K ohm resistor, a 3.9K ohm resistor, and 8.2K resistor. So since this is the first time that we've used these resistors, I've gone out on the internet and tried to find you a resistor with the same color bands. So if you're looking at this on the internet on your computer monitor, they will be in full color. We just have to remember that the bands for a 2K resistor are 20 followed by 10 to the power of 2. So that would be 2000. So that would be 2000. Probably going to be a gold tolerance band. The 3.9K is going to be orange, white, red. Probably again with a gold tolerance band. And the 8.2K resistor is going to be gray, red, red. Again with a gold tolerance band. So the first thing we're going to do is use an ohm meter to check the values of the resistor and record your values under equipment. Now the reason we're doing that is to make sure that you've picked up the correct resistor. So to use the DMM as an ohm meter, we rotate the dial around till we get to the ohm symbol. The red lead goes in the red terminal labeled ohm. The black lead goes into the common terminal that is black. Doesn't matter which way around our resistor goes, but it's important to use the alligator leads so that we don't touch the resistor, changing the resistance of the resistor. So this is my 2K ohm resistor, and you can see my reading is 1.972 K ohms. So my next resistor is the 3.9K ohm resistor, and you can see it reads 3.83 K ohms. And this is my last resistor. It's supposed to be 8.2 K ohms, and you can see that it's actually 8.29 K ohms. So remember to record those results underneath equipment. So once you've figured out which resistor is which, I recommend sticking it into a small piece of foam so that they don't roll all over the place. And this is my 2K, my 3.9K, and my 8.2K. So now I don't have to fumble around trying to figure out what the color codes are on them. I just have to put them in my circuit one after another. Under procedure, step number 2, we're to build the circuit of figure 4.1 using the 2K ohm resistor. We're going to set the DMM to measure DC current and insert it in line between the source and the resistor. We're going to set the source for 0 volts. We're to measure and record the current in table 4.1. It says note that the theoretical current is 0. And any measured value other than 0 would produce an undefined percent deviation. The power dissipated by the resistor should also be 0 watts. Now figure 4.1 is going to be our schematic for today. You can see that I have a power supply over here, and we're going to get up to 12 volts out of it. It's a variable power supply, so we can get, on our power supplies, we can get 0 to 20 volts, but here they want us to go from 0 to 12 in 2 volt increments. I've labeled the terminals that we're going to be using. So for the positive terminal, that's going to come out of the red terminal labeled plus 20 volts. And the negative terminal is going to be coming out of the black binding post, and it's going to be labeled COM on the power supply. We're going to be using an ammeter because we want to check the current that's going to flow through our resistor. So on our ammeter, we have a positive side and a negative side. So on our ammeters, we have the red side, and it's going to be a red hole labeled MA for milliamps. And on the other side, it's going to be the black terminal labeled COM. And this is the first resistor we're going to be using. So we're going to be using a 2K ohm resistor in the first case. So I just wanted to show you that this is my power supply, and I am putting 0 volts in, and this is my ammeter, and I am getting 0 milliamps out of it. And this is my circuit on the trainer. You can see I have one resistor in here. So I want to show you how I wire that up. So the first thing I want to show you is this is my 2K ohm resistor. I've got one leg going into this hole and one leg going into that hole. Now these buses are connected across here, so 5 holes are connected together. So I've got the black lead going into the same group of 5 holes as the lead for my resistor. Then over here you can see I have the other leg of my resistor and the red lead, and they go into the same group of 5 holes. So this red lead is making contact with my resistor lead, and this black lead is making contact with my resistor lead. Now it doesn't matter which one of the 5 holes I put the resistor lead in, and it doesn't matter which one of the 5 holes I put the black lead in. Obviously they can't both go in the same hole. Now some students try to wire up their circuits like this. The problem is the red lead does not make contact with the resistor leg, and the black lead does not make contact with the resistor leg. To make electrical contact, they have to be in the same row. So the same group of 5 holes connect the 5 things together. So here we're just connecting the black lead and the resistor lead. So the black lead is connected to the resistor lead. Here the red lead is not connected to the resistor lead. I've moved the red lead. It's now in the same row as the resistor lead, so it is now making contact in the breadboard between the red lead and the resistor lead. Doesn't matter that I've left 3 spaces here, and over here I have no spaces. I've left the spaces on the other side. Doesn't matter. It's just that the 5 holes are connected together. These are called 5-way binding posts, and they unscrew and the wire goes in. It's very, very important that you screw down on the bare metal wire. A lot of times students will put the insulation underneath the terminal and squeeze down on the insulation. The insulation does not make contact to the metal. You have to go bare wire into the binding post. So it's always a good idea to leave a little bit of bare metal sticking out so that you know that you're not clamped down on the insulation and you're making good electrical contact. Now, to wire all these components together, you need to follow your schematic. And what we're going to do is we're going to go from the positive of the power supply, so that's out of the 20-volt terminal. So take a red lead, and out of the plus 20-volt terminal, we're going to run the lead to our ammeter, and we're going to put it into the milliamp hole. So you can see on my schematic I've highlighted the red lead that we've just put in, and that went from the plus 20-volt hole to the red milliamp hole on our ammeter. Next we're going to go from the ammeter to our 2K ohm resistor. So that's out of the black COM hole. So from the black COM hole, we're going to go over to the red input to our resistor. So you can see on my schematic I've highlighted that red lead that we went from the black COM hole on the ammeter to our resistor. Now we're going to go from the resistor all the way back to comment on our power supply. So I'm going to take a black lead, hook it to the terminal on the trainer, and bring that back to the black COM binding post on our power supply. So I've just run the black wire from the other side of our resistor all the way back to the black COM binding post on our power supply. Do not worry about this ground symbol. It's required for multi-sim to run a simulation. So under table 4.1 for the 2K ohm resistor, I've recorded our current measurement as 0 milliamps. The formula that we're using to calculate deviation was given to you in lab number 3. So please remember that percent error, or deviation, is going to be equal to the absolute value of the theoretical value minus the experimental value divided by the theoretical value times 100. So for table 4.1, the deviation will be 0% and the power will be 0 watts. Under procedure, step number 3, we're going to set the power supply to 2 volts and determine the theoretical current based on Ohm's law and record this in table 4.1. We're then to measure the actual current, determine the deviation, and record these in tables 4.1. We're to use the measured current to calculate the power dissipated by the resistor. So on table 4.1, the first thing that we're going to do is calculate our theoretical current values, and then we're going to measure them using the circuit that we've just built. We're going to calculate the percent deviation, and then we're going to check the power dissipated by the resistor using the measured current. So to calculate the current, what we're going to do is use Ohm's law, and Ohm's law says V equals IR. So rearranging the formula, I equals V divided by R. So we know that R is going to be 2K. So we take 2 volts, divide it by 2K to come up with our current at 2 volts. So for the instance where we have 2 volts, the current is going to be 2 volts divided by 2K. So to enter that on our calculator, we press 2 divided by 2 exponent 3 equals. So you can see on your calculator we have 2 divided by 2 times 10 to the power of 3. This is not exponent 3, it's not 2 to the exponent of 3, it's 2 times 10 to the power of 3. So that's what that EXP button does on your calculator. And you can see that if you put your calculator in engineering notation, like I showed you last week, we end up with 1 milliamp. So you can see I have my power supply set at exactly 2 volts, and the current reading on my ammeter is 1.01 milliamp. Now this is on the 40 milliamp range. If I go down to the 4 milliamp range, you can see I get a different reading. So on the 4 milliamp range, I'm getting 0.967 milliamp, or 967 microamps. The reason for this is because the internal workings of the ammeter is a different resistance depending on what range you set your meter to. So for the meter to be on the most accurate range, it must be on the 4 milliamp range. And here we can see we've got 0.967 milliamps. So in your table, record 967 microamps. So to calculate deviation, once again, we're going to use the percent error formula from lab number 3. So in our case, we're going to take the absolute value of 1 milliamp, which is our theoretical value minus the 967 microamp. And remember to keep the order of operations when you're doing this on a calculation. You may need to put brackets around the 1 milliamp minus the 967 microamp, and then divide it by the 1 milliamp. Then take the positive value you end up with and multiply it by 100. So on your calculator, put in the left bracket and type in 1 exp, and this is milliamp, so that's 3, and you want it to be minus, so press the plus minus button, and then we're going to subtract from it 967, so 967 exponent, microamp is 6, so press the plus minus button. And then you want the right bracket. And then we're going to divide it by the 1 milliamp. So you want exp 3 plus minus. And then it's times 100. And that's equal to 3.3%. So in table 4.1, I've now recorded my deviation as 3.3%. I'm now going to calculate the power dissipated by the resistor. So remember, the formula for power is equal to voltage times current, and we're to use the measured current, so we're to use the 2 volts and the 967 microamps. So to enter the power calculation on your calculator, type in 2 times 967 exponent 6 minus equals. So on your calculator you have 2 times 967 exponent, remember that's times 10 to the power of, minus 6, which is micro. The answer is 1.93 milliwatts. So in table 4.1, I've recorded my power as being 1.934 milliwatts. I just want to remind you that we are using quarter watt resistors, so 1/4 of a watt is equal to 250 milliwatts, and our resistor is only dissipating 1.9 milliwatts, so it's well within the safe zone. Under procedure, step number 4, we're to repeat step 3 for the remaining source voltages in table 4.1. Now moving on to the other voltages in the table, I've already given you a complete demonstration of the calculations at 2 volts. I'm going to leave you to do the calculations for 4, 6, 8, 10, and 12 volts. So on table 4.1, I've completed my I theory calculation for 4 volts, 6 volts, 8 volts, 10 volts, and 12 volts. I'm not going to bother showing you how I do I measured, because I've given you an example of that at 2 volts. So you just need to increase the voltage on the power supply. That's the plus 20 volt terminal. So increase it to 4, 6, 8, 10, and 12 volts. And remember, you may need to change the range setting on the ammeter if the current actually goes above 4 milliamps. I'm going to leave you to calculate percent deviation and power dissipated by each of the resistors. In procedure, part 5, we're going to remove the 2k ohm resistor and replace it with the 3.9k ohm resistor, and repeat steps 2 through 4 using table 4.2. So So table 4.2 uses the 3.9 k ohm resistor, and then we're going to repeat steps 2 through 4 for the 2 volt, 4 volt, 6 volt, 8 volt, 10 volt, and 12 volts. I've completed my calculations for I theory for table 4.2, so now we've doubled the resistance up to 3.9k from 2k, and we can see that the current is going to start at 0.5 milliamps, 1 milliamp, 1.5, 2, 2.6, 3. So for procedure part 6, we're going to remove the 3.9 k ohm resistor and replace it with the 8.2 k ohm resistor, and repeat steps 2 through 4 for table 4.3. So you can see table 4.3 is for the 8.2 k ohm resistor. So we're going to start with the 2 volts and work our way up to 12 volts. And finally, I've completed my calculations for I theory for table 4.3. That's the 8.2 k ohm resistor, and you can see our current starts at 0, goes to a quarter, a half, 3/4, 1, 1 1/4, 1 1/2. For part 7 of the procedure, we're going to be using the measured currents from table 4.1, 4.2, and 4.3 to create a plot of current versus voltage, and we're going to plot all 3 curves on the same graph. It reminds us that voltage is the horizontal axis and current is the vertical axis. So you can see in your lab I've given you a piece of graph paper, and we need to name the axes. So voltage will be on the horizontal axis, current will be on the vertical axis. So if voltage is on the horizontal axis, we need to label each of these squares. Each square could be 1 volt, 1 volt, 2 volt, 3 volt, 4 volt, 5, 6, 7, 8, 9, 10, 11, 12, 13. So we could label the bottom axis by 1 volt increments. Then you'll have to check your readings to decide if each one of these will be 1 milliamp or will it be 500 microamps. It all depends on what the maximum current that we're trying to plot is going to be. And we need to plot the results for each of the 3 resistors. So I've labeled the axes of my graph. So the horizontal one is going to be voltage, and I've determined it's going to be in volts. So my scale is going to go 0, 1 volt, 2 volt, 3 volt, all the way up to 12 volts. Now over here on the vertical axis, that's going to be current, and I've determined that that's going to be in milliamps. And I need to get to a maximum of 6 milliamps, so I've decided to draw my chart as 2 squares being 1 milliamp. So 1 square would be half a milliamp. So my scale goes every 2 divisions is 1 milliamp. So 1 milliamp, 2 more is 2, 2 more is 3, 2 more is 4, 2 more is 5, 2 more is 6, 2 more is 7. So for table 4.1, at 2 volts, my first current reading was 1 milliamp, so I've put a dot. At 4 volts, my reading was 2 milliamps, so I've put a dot. At 6 volts, I was at 3 milliamps. At 8 volts, I was at 4 milliamps. At 10 volts, I'm at 5 milliamps. And at 12 volts, I'm at 6 milliamps. So using a ruler, line up all the dots as close as you can and draw your first line in. So label your first line 2K ohms. Then we're going to plot the points for table 4.2. draw its line in as fitting the points as close as possible. So the second line is 3.9 k ohms. Then we're going to put the points in for table 4.3. That's the 8.2 k ohm resistor. Draw the line so it fits through as many points as possible. Now we're going to label this last line as 8.2 k ohms. I've given you 4 questions to answer. So once you've completed your graph, you can answer the questions. I know some of you are having difficulty answering these questions, but we're looking for fairly simple answers. So does Ohm's law appear to hold in this exercise? Well, looking at your graph, you can see that we have the 2K, the 4K, the 8K. So as we increase resistance, the current decreases. So I think the law holds. Question 2, is there a linear relationship between current and voltage? We have these straight lines. Straight lines seem to indicate linear. Question 3, what is the relationship between the slope of the plot line and the circuit resistance? So please remember, when you're looking at the slope, what they talk about is the rise over the run gives you the slope. So it's the angle that the line is moving at. So you can see the steeper the slope, the lower the resistance, the higher the current. The lower the slope, the higher the resistance, the lower the current. And the last question, did any of the voltage resistor combinations exceed the power ratings of the supplied resistor? So to find out if any of our voltage resistor combinations exceeded the power ratings of the supplied resistors, you're going to have to do the calculations on each of the table and make sure that none of the power dissipated by the resistor exceeded 1/4 watt or 250 milliwatts. So when you've completed the lab, show it to your instructor so that they can initial it to indicate that it is complete.